Okay, it didn't. Okay. All right, so you can try to ask questions if I'm not being clear about something, and that will help to uh, make the lecture better, I hope, to guide the lecture a little bit. Okay, so without further ado, I'll just start the lecture. Okay, so this is our first. Did you have a question? Sorry? Okay, well, can you see it now? Can you see the board? Oh, does the computer only show me? Ah, okay, well, let's see. Maybe it's a double thing then. Oh, I see. Oh, that's not that great. I would like the computer to be using the this thing here. Okay, let's see. Let me try this. Can you see the board now? Okay. All right, I'll try to write big, and in any case, there's going to be a video of this later, which I'm recording. Okay. And there's probably a way of integrating these things as well. Okay, so the first lecture is going to be on functions and function notation. All right, this is chapter 3.1 of the textbook. Okay, so functions and function notation. You can't see? All right. Okay, the video should be much more visible. So I'm just going to have to continue on because I don't know how to put the two together right now. So I'm sorry, this might not come out very good on Skype right now. Okay, so I'll start with this. You can, when I read it, you can see what's going on, right? Or you can at least hear what I'm saying. Okay, some of you have something going on in the background. I'm not sure what that is. Oh, it's me maybe. It's refocusing on, okay. All right, okay, so now the first thing I want to tell you about is relations. So a relation is a set of ordered pairs. So an ordered pair is a pair of numbers A and B, like this. And you use these curved brackets or parentheses with a comma in between. All right, so they're ordered because it means something that A is the first entry and B is the second entry. You can't just interchange them or change the order. There's always the first element and the second element. Or in graphing, you usually call the pair X and Y. So X will be a value along the x-axis, as measured along the x-axis, and Y will be a value measured along the y-axis. So a set of ordered pairs will be a set of numbers like this. And I'll call the first relation simply R, little r. Can you see that? Okay. And R is given by this set of ordered pairs. So we use set notation, which are these curly brackets. 1, 2, 2, 3, and 3, 4. So this is an example of a relation. Okay, so in each case you have an ordered pair, a first element and a second element, a first element and a second element, a first element and a second element. And then you have three such pairs, and that is called a relation. All right? Now the domain of a relation is simply the set of first elements of each pair. So the set of first elements will be, and it's called D. So I write a curly D. So in this case, D is the set 1, 2, and 3. So the set of elements consisting of just 1, 2, and 3, because those are all of the first elements in each of the ordered pairs. And the relation, or the range, as you might think, is the set of all second elements. So what is it in this case? All right, can you all see that? Okay. 2, 3, 4, yes. There you go. All right, so this is the idea of a relation. Now a relation can be any set of ordered pairs that you like. That will be called a relation. And the domain will then be all the first elements of that relation. The range will be all the second elements of that relation. Usually you'll have numbers in this class. X and Y will be real numbers, or integers, or rational numbers, and so will Y. But sometimes X will be, a more abstract thing, like the name of a person. Anyway, it's more abstract in the sense that you can't put a number to it. Okay, so for example, the height of a person, you might have the domain would be the names of the people, and the range will be the real numbers that represent the heights of the person. Okay, now there's various examples that I want to point out here for different types of relations. You can have other examples which I'll put down as well. So let me just make some room here. Okay, so you're welcome to take notes. Sometimes it's helpful to write this down as you go, since it helps you to remember it for later. Okay, so anyway, so another example would be S is a relation 1, 1. I was going to put 2, 1, and 3, 1. Oops. So you have to have a open and a closed curly bracket, and these are the parentheses. Okay, so this is 1, 1, 2, 1, 3, 1. All right? Or another one would be T. 1, 1, 1, 2, 1, 3. Okay, so here we have three different examples. R, S, and T are three different examples of relations. Now, R and S have a special property that's different from T. And we call this special property, we'll call this special property a function. The relation will be more than just a relation. Well, it will be a special kind of relation called a function. Now that special property is that for a function, every value of x has just one value for y. So each different value of x has precisely one value for y. So a function basically is a relation where each first element has exactly one second element associated with it. Okay, another way of saying this is it's a rule. A function is a rule which assigns to each value in the domain a single value for an element of the range. So for example, this first relation is a function. For each value of the domain, for each value in the domain, you have just one value for the range, in the range. So 1, you think of 1 as giving you 2, and 2 gives you 3. And then 3 gives you 4. Okay, so you can think of the mapping as drawing arrows from the particular values from the domain to the range, like that. Or this way, like this. I put the domain here and the range here, and I put arrows mapping from 1 to 2, 2 to 3, and 3 to 4. So each value here has just one ending value. There's only one arrow going from 1 over here. All right. Likewise for S, that's R. So for S, we have 1, 2, 3, and we go to 1. So here, again, each value of X has how many values of Y? No. Each value of X, so 1 is associated just with 1. 2 is associated just with 1, and 3 is associated with 1. Okay, so each element in the first position has just one second element associated with it. But let's look at this. T only has one element in the domain. It's the same one every time, and 3 elements in the range. So I have to draw 3 arrows from this element to represent the entire relation. So this is a relation, but not a function. Okay, because there's an element in the domain which has 3 values associated with it. 3 second values associated with it. Okay, does that make sense? Okay, so these two are both functions. So this idea of a function is an important one for mathematics and what we're going to be doing. So it's important to be able to tell when a relation is a function, and we'll see also how to do this using tables and graphs. Okay. I'll erase our example here. Okay. So another way of viewing functions is you look at them in terms of input and output. So the input values are elements of the domain, or from the domain, and the output values are all the values you can get, namely those in the range. All right, so you can take an element in the domain X, and you basically put it into you can think of it as a box called F. F will represent the function, and out comes Y in the range. That's supposed to be an R. Oops. And we'll use this notation. So I start with x, all right? And now I put it into this box f. And mathematically, the notation is you put brackets around it, and f sort of encloses it, f kind of operates on it, all right? So you stick, in other words, you stick the x value into the box. It's represented by these parentheses, and out comes y, okay? So the value, after evaluating this function, is going to be called y. So this you could say y is a function of f. You would write it that way, or you'd say it that way. Or you could say f at x is equal to y. F at x equals y. All right, I evaluate the function f at x, or f of x. You could also say f of x. Okay, so have you heard of this before? Have you heard some of this before in previous classes? Okay. Math 101, yeah. So you've probably seen this in Math 101, yes. So some of this is a review. Okay, so, okay, actually, could you please turn off your audio, turn off your mic so you can still hear me, and just turn it on if I ask a question, okay? Or if you want to interrupt and ask a question, because it seems like there's some sort of noise in the background, but I'm not sure where that's from. But it might be. It's a little bit distracting. It might be picked up by the video. I don't know. Okay. All right. So, thanks. Okay, so there are various examples in the textbook. Yeah, I'll just stop. I'll erase some things here. So if you check out the textbook, they have example one here, which gives you, price as a function of item. So they give you a table of items and then the price. Okay, so some items might be, I don't know, cheese, rice, fruit, let's say. So maybe apples or something. An apple, a bag of rice and cheese. So some of these could have similar prices. Let's say $4. This might also be $4. Apple might be $1. I don't know. It's kind of expensive. Actually, you buy them in bulk and less expensive that way. Or a bag of apples, maybe $3. Okay, so is this a function? We can ask whether price is a function of item, and it is, because every distinct item for x has a single value for the price. So price, you'd say price is a function of the item. But on the other hand, going the other way, the item is not a function of the price. Because you can have for the same value of this price, $4, f of 4 is equal to cheese. So it has two possible outputs, if you like. Two possible values. All right? So this is an example of, that's an example of something which is not a function. It's a relation but not a function. Okay? And another example which you could look at is GPA of students. So look at the textbook example, and they show you that you can have kind of a range of, if you go from your average percent grade for all your classes, right? That might be in a range 80 to 89 or something, whatever. And that means, you know, the average of all your classes is in the B range or something like that. But the value B, or B minus or B plus, has several possible percentages associated with it. So the GPA is a function of the average percent grade. But not the other way around. So the average percent grade is not a function of the GPA. I could write it like this. GPA is a function G of the average percent grade. Just like price. Price is a function of item. I should write it like that, so that it's consistent with this way. But it's not a function of, it's not a function the other way around. Okay, and another example they give you it's a try it out question. Try it, number 1. The players are ranked, like baseball players are ranked in order of their greatness, I guess. So each name gets a number. First it's Babe Ruth, and he gets a number 1, and so on and so on. Then you have Hank Aaron is number 5. And that is a function going both ways, because for each name you have a single number. For each number you have a single name. Okay, so that's a function going in both directions. Okay. Another way of writing this function notation is, instead of writing y is equal to f of x, you can also write f, and then you put a colon here. It maps x to y. So f maps, you read this as f maps x to y. That's the way you would say it. So this is a bit more. This is a bit more what they use in upper and higher mathematics. Okay, another example is the number of days in a month. Each name, January, February, March, April, has a unique single value associated with it, namely the number of days in that month. So January has 31, February has 28. Oh, maybe it could have 2, right? If it's a leap year, it might have 29. Okay, so for a single year, if you give the year, and you know it's not a leap year, then it should have 28 days. So then it's a function. And March has 31, April has 30, and so on. So each name has a unique number associated with it, whereas it's not true the other way. So each number might have several different names associated with it. 30 days is April, June, and November. April, June, and November, right? And 28 has only February. Okay. So using tables, you would write normally the input value in the first column and the output value in the second column. Okay, so as an example of a table, I would put in for my function r, my relation r, which turns out to be a function. I get this table, 1, 2, 3. Those are my values for the input, or the values in the domain, and 2, 3, and 4. So you can see that this function just adds 1 to every value of the input and gives you the output. So one way of writing this is r of x is equal to x plus 1, if you want to write something algebraic there. So in other words, I could call this input is x and the output is y. Similarly, t, x and y are here. So t, all the values 1, 2, and 3 give you 1. So this function will turn out to be, it's just the constant function 1. So whatever number I put in for x, the output is 1. Okay. But the other one, the s is not a function there, so I can't use this function notation. I'll only use this function notation when I do, in fact, have a function. All right? So, sorry, this was s, right? This was s. And the last one was t. So t would be taking the single value 1 to a possible set of 3 values. So it's not really correct usage of this notation, because this really only is supposed to refer to a function. You plug in one value, you get one value out. One value in and one value out. Okay. So any questions on this so far? No? Okay. Okay. Remember, turn on your mute button. Please mute your, because I can hear a bit of static in the background. Just wondering if that's the noise in the background, or can you both turn off your mute buttons for a second, please? Okay, I turned it off, so maybe it's at my end. Can you hear me? I muted both of you actually, but. Okay, can you hear me now? Okay, all right, okay, there's a bit of, I don't know if it's the software or something, but it's a little bit, sounds a bit funny. Okay, so back to our lecture. Okay, we use a lot of algebra here. So most of our functions will be able to describe the rule in terms of an algebraic relation or an algebraic expression. So for example, function f of x is equal to 3 minus x squared. Okay, so what this means, it's important to understand what this expression, what this whole thing means, because we're going to be using this a lot in this class. Okay, so what I have here is f is a function of x. All right, that's what this notation means. And it's given by, it's equal to this particular expression for x, in terms of x. So it's not x itself all the time, but it's some expression involving x. So what this means is, given a value for x, in order to find the value of the function, I simply have to plug that value of x into this expression and evaluate. And that gives me the value for f of x, or the value for y. That's right. So I can also write it like this. Y is equal to f of x is equal to 3 minus x squared. Okay, so for example, plug in different values of x. So evaluate the function f at these different values. So let's say 1, 3, b would be find f of a plus h minus f of h, f of a over h. So this is a is a some letter, not this symbol a, indicating the part of the question. Okay, so if I evaluate, I take this will be the value for x. All right, so I plug it into the function. So I put it into the parentheses. Remember, parentheses does not mean multiply here. It means the input to a function. Okay, so you have to do whatever the function tells you to do in terms of the algebraic operations to get the output. So here you plug it in where the x is. So if you're not sure what to do, just put brackets where the x is, and then leave it blank, and then put the number in later. So it's 3 minus 1 squared, which, and you follow the order of operations. Remember, order of operations says you do the exponents first, so you square 1, and then you subtract 3 minus 1, and that's 2. Okay, similarly for b, you would take f of evaluated at 3, and then you get 3 minus, okay, so you have to again be careful here, it's 3 squared. So you don't subtract 3 minus 3 first and then square, right? You get just 0, which is wrong. But you should first take 3 squared, leave the rest alone, that's 9, and then you take 3 minus 9, which is minus 6. Okay, so that's how you get b. For c, I simply have to evaluate x. X is now equal to a here. So f of a is very straightforward. You just plug in a for x. So it's 3 minus a squared. And here you don't have to do anything more. It's just because you don't know what a is. Okay, and you can leave it in this simplest way. It's already in the simplest form. Okay, now this final one, where you first evaluate the function at a plus h, and then you subtract the function evaluated at a. Oops, hello? Oh, hello, Arifa? Hello? Okay, can you hear me? Okay, we got cut off somehow. Okay, so you're back? Okay, Zahra's not here yet, so... okay, anyway, I'll continue on with the lecture. I'm still recording here. Okay, so to find this expression, d, first I evaluate f at a plus h. Okay, so I plug in, wherever I see the x, I plug in a plus h. So I put the a plus h in brackets. So I have to square the a plus h first, and then take 3 minus that. Okay, so I have to follow my order of operations and also use the distributive law here. So this is a squared plus, remember what a binomial squared is? Square of a binomial? A squared plus 2 times the product of the middle of the terms plus h squared. So the first squared plus the last squared plus 2 times the product of both of them. And I have a minus sign in front. So when I expand this, I have to put the minus sign in front of every term. Okay, so 3 minus a squared minus 2ah minus h squared. Now I have to subtract, I have to find this whole expression here. So now I have to take f of a plus h minus f of a, all right? And then divide the whole thing by h. Okay, this is an important quantity here in calculus. It's expression that's used to find derivatives, just to let you know. But for now, we won't concern ourselves with that. So minus the value for f of a, which I wrote here. So I'm going to have to use brackets, and I have to watch my brackets because I'll now change this to a plus sign. This will be minus. So if I eliminate the brackets, then this will be minus, and this will be plus. Okay, sorry, that's kind of a quick way of doing it, but now I can calculate 3 minus 3. So those cancel because they have an opposite sign. I add them. And these have opposite signs, so they will cancel. And then I have to divide the whole thing by h. And you see that all these terms have an h in them. So when I factor this, I'll get minus h outside of 2a plus h divided by h. Cancel that, and the minus side stays there, and I get minus 2a minus h. So that's all one expression. Okay, can you all see that? Can you see that? Okay. I don't know where Zara went. It's just you, Arifa, right now. So, okay, I guess they can join. They can join you if you have you joined? Zara, have you joined? We just see you're just there. I see. Okay. Okay, just see Arifa here. All right. Okay, so then, so let's see some other examples of functions. Okay, now you might have this kind of function. So this is called a linear function. Okay, or let's see, another one would be x cubed minus 3x. So that might be another function. I'll call it by a different name, g of x. Okay, so another might be call it h of m. You might also have square roots in there. So it's m minus 3. Okay. And evaluate, say the question is evaluate h of 7. Okay, so again, the way to evaluate a function at a particular value of m is you plug in that value for x, or in this case m, into the expression and evaluate that. And remember, you have to use the correct rules. All right, so they don't change just because you have this new function idea or notation. So you put the 7 where the m is, and you get 7 minus 3. Now, since that is all under this square root sign, that acts like a bracket, so I have to do that first. Okay, I can't separate the square roots and then subtract. That would just be wrong. You never get the same value if you do that. All right. So then you take 7 minus 3 first, and that's the square root of 4. Plus, in this case, it's much easier. It's just the square root of 4, which is 2. Okay. This represents only the positive value of the square root, remember? The square root sign. If I wanted the negative square root, I would have to write that as a negative sign in front. So let's say h, if I call this h plus, and this h minus, the h minus might have this 4. Oops, put an m in there. Okay. Now also solving, we're now at example 8 in the textbook. suppose you're given a function. So let's say this function h of p is equal to p squared plus 2p. All right? Then you want to in some cases you want to find out, given a value for the function, what values of p would I have to put into this function to get that value? Okay, so evaluating gives you always one answer, right? Because if you know the value of p that you want, you just plug it in and you'll automatically get one answer for the function. That's by definition of the function. But if you want to go the other way, if you know the value of the function and you want to find out what the value of p initially is, then that requires solving an equation or some expression. Okay, so that's called a solve question. So solve for HP equals 15. All right, so what I do is I just use this expression, find all the values of p for which this equation is true. So I equate this expression to that value, and then I find all values of p for which this is true. Now you can see this is a quadratic equation. So I could do it by the usual method. Okay, so I put everything on one side of the equation and make the others, so the other side is 0. Okay. And then I factor both sides, I factor this side, right? So to find two factors so that, this is not going to work, or is it? Yeah, well. So two factors such that when you add them together you get 2, and when you multiply them together you get minus 15. And the first parts of these two factors will both be p, right? So I'll have to have 2 with different signs. One will be plus 5, you can see it's by checking a few values, right? And minus 3. So 5 times 3 is 15. You look at all the factors of 15, remember? Yeah. So 1 of 15 is a pair. 3 times 5 is another pair. And then right away that you can see that's going to work, not the other one. So then because they're opposite signs, you'll subtract them and use the sign of the bigger. You assign the plus in this case to the bigger value, so you get a plus sign here. Okay, now to solve this equation will be true when just one of these factors is 0. So this implies either p is equal to minus 5, p plus 5 is 0, or p is equal to minus 5, or p minus 3 is equal to 0, or p is equal to 3. Okay, so the solution set you would write down is minus 5 and 3. And you should check that. Remember, always check your answers. So if I plug in minus 5 into here, I get, right, minus 25. Quantity squared is 25 plus 25. Plus 2 times minus 5 is minus 10. So 25 minus 10 is 15. That's correct. And 3, if I plug in that, 3 squared is 9 plus 3 times 2 is 6. 9 plus 6 is 15. Yeah, that's correct too. Okay. And do I get any other solutions? No, because a quadratic can only have at most 2 real solutions. Okay, so that's all the solutions we have. They both work, and so that is our solution set. All right. Another example would be using the square root function. Okay, so this should be a review of Math 101 stuff. Hopefully, more or less. So this is similar to the try it 5 question, try it number 5 in the textbook. G of m is square root of m minus 3. And I want to solve for gm is equal to 3. Okay. All right. So again, there's no, you can't do any cancellations here. You know, don't think in terms of canceling or trying tricks or anything. So you simply write the expression down, equate this to this, so it's square root of m minus 3. So the expression you write down, expression for g, and then you write down the particular value it will take on in this case, which will be 3, and you equate those two. Okay, and then you solve this equation using the usual methods. All right, so remember the usual methods are you can do both things to each side of the equation at the same time. You can subtract the same thing from both sides of the equation at the same time. You can add the same thing to both sides at the same time. You can multiply both sides by the same number. You can take the square of both sides at the same time. That will also keep it an equation. Okay, but at the end, if you do that with a square, remember, with square roots, you still have to check all your solutions, because you might have included one which is not a solution of the original equation. Okay, so you square that, and you get m minus 3 is equal to 3 squared. Okay, so I square that, and it's 9. And then, okay, so I square this side, and I get back the original argument, m minus 3. And I square this side, and I get 3. Square both sides. All right, and now I can solve for m just by adding 3 to both sides, and I get 9 plus 3, which is 12. Okay, and now check that. It's always nice to check, because it's sort of, if you made any mistake, you know right away. So check doesn't work, and then you can look for it, and it's really satisfying when you either get it right the first time, although that doesn't happen very often with me anymore. But if you get it right the first time, great, it works. You check it, and you can see it's correct, right? Or if you don't get it right and you find a mistake, that could even be possibly even more satisfying. But anyway, that's what I end up having to do. But you check it. Is g of 12 equal to my value 3, to the value that I want? You just plug in the 12 in where you see the m, and you get 12 minus 3, and then you take the subtraction of that, and that's 9, and then you take the square root, and that's 3. So yes. Okay, now you can see that if you put a minus sign in front of the 3, in this case, if you try to solve for the equation, yeah, so in the end, what's the solution? I should write down the solution set. The solution set here is the value for m. All the values for m which make this equation true. So that's a solution set. Just one value. Or you can write it if there's just one value, m equals 12. Now, but if I try to solve this equation, what happens is that I'll equate this side to minus 3. I'll square both sides, and I'll get m minus 3 equals, this will now be plus 9, because I square this whole thing. Right? And then I'll still get the same possible solution as before, but what happens when I plug it back in? When I plug it back into the original equation, I get 12 minus 3, which is 3, and that's not equal to minus 3. Remember, this is the positive square root all the time. So the answer is actually no solution. So that's the solution set, the empty set. Okay, so you have to be careful about things like that. Always check your answers to see if they're all in the solution set. Okay. Now there are quite a few, besides drawing a table, there's also the way of graphing, a way of showing what the function means by pictures. And graphing can tell you a lot about a function. So it's important to understand what these concepts mean in terms of graphs. And so an example here, yeah, this is also, what I'm writing down is an example of an implicitly defined function. So if I write down this kind of equation, so it's an equation in x and y, then it's, if you recall from Math 101, it's going to be the graph of a straight line, right? Now, this will also turn out to be a function. It will define y as a function of x, I should say. All right? Now you can show it as a function of, show y as a function of x simply by solving for y. Okay, so this is an implicit function, implicitly defined function. But I can find an explicit form for it, or explicit expression by solving for y. So then I put everything else on the other side from the term with the y in it, and I get 3y minus 2x. And then I make the coefficient of y1 by dividing by 3 on both sides. So I get y is equal to minus 2 over 3 times x. Okay, so now I can call this a single function f, like this. Minus 2 over 3x. Okay, I'm going to go another 15 minutes. Let's see, it's about 5 o'clock your time, right? So anyway, I'll go another 15 minutes to try to at least get into a little bit into the graphing, using graphs with functions. Okay, so how do we represent this function graphically? Okay, well, as you know, it's a straight line. So I should call this representing functions using graphs. Okay, so we draw our axes. I have to draw them a bit closer together here. 1, 2, 3, 4, 5. Let's say 1, 2, 3, 4, 1, 2, 3. Actually, it's something like that, yeah? 6, let's say. So this is 3 and 6. This is x. This is y. This will be 2, 4, minus 2, minus 4. All right, so you can write it as a table of values. And really, you just, for a linear function, you just need how many points? How many points to draw the graph? Just 2, yeah. I think that's what you said. So 0, 0 would be 1. All right. If you put in 0 here, you get 0 for y. Another easy number would be 3. So if you plug in 3, you get 3's cancel, and you get minus 2. Okay, or you can choose minus 3 and get 2, and that's okay as well. So like that. And then that can be used as a check. So you draw those points and you try to draw a straight line here. You can check at another point here, so 6 and minus 4 should also be in the set like that. Okay, so this function now is now the rule which gives you for each value of x, we pick a value of x along the real axis here, the x-axis here, and you would just drop down immediately, go straight down until you hit the line, or go straight up if that's where the line is. So you go along a vertical line, up or down, until you hit the line, and that gives you the y value for that point is the value of the function. So this is our value for x, and this is our value f of x. probably didn't get it right there, but 4 would give you minus 8 over 3, so something in here. 2 2/3. Okay, so that's a graphical representation of the function. The x values will always be measured along the x-axis. So if you change the x value, you move along the x-axis. And then the y value is simply the y-coordinate. So you measure that along the y-axis. So here for positive values of x, I'll get negative values for y. For negative values of x, I'll get positive values for y. Okay, circles. Okay, so let me now erase all this here. Erase this. Okay, so part of your review might have taken you into circles. Okay. In this case, I'll look at the unit circle. Okay, so recall geometrically what a circle is. So if you haven't heard this before, I guess it'll be new to you. So a circle is the set of points which are the same distance from a single given point. Okay, so it's a set of points which are equally distant from a single point on the plane. Okay, so the idea is here you have a starting point, and then you take a fixed length, such as you would get if you use a compass, a pair of compasses. You fix one point and you draw the other one all the way around, and that gives you a circle. So that fixed distance is called the radius, and the point in the middle, which will be given usually by hk in Cartesian coordinates, so that's if you draw a graph of that, that's called the center of the circle. So what it means to say that the distance from the center to the point on the circle is always fixed. So here's what that is saying. So x and y will be variable numbers, both. They will vary in some way. That will be an arbitrary point on this circle. H and k will be two fixed numbers, an x-coordinate and a y-coordinate of the center point. That does not change. Those two values don't change. Now to find the distance between the two, you use the distance formula. And the distance formula is found by Pythagoras. Pythagoras' theorem, which is, anybody remember that? So for a right angle triangle, if A and B are the short sides of the right angle triangle and C is the long side, C is called the hypotenuse, then C squared is equal to A squared plus B squared. Or if I take the square root, C is always positive, so I take the positive square root and I get A square root of A squared plus B squared. All right. Now in this case, if you look at the coordinates if you look at the points in a Cartesian representation here, I have h and k down here and x and y up here. Okay, so the length of this side is going to be the difference between x and h. So this side will be x minus h. Actually, if x is on the other side, then it would be negative of that expression. But I can always make it positive by taking the absolute value. Okay? And this side will be absolute value of y minus k. All right? Now when I square both sides, the absolute value signs go away, because if there's a minus sign, it will be canceled. So the distance here which is c in this case, is the square root of x minus h squared plus y minus k squared. So I take the differences first, x minus h and y minus k, then I square those separately, right? And then I add those squares. And then I take the square root of everything. Okay, and now I want to equate that to the radius. That's going to be equal to the constant radius, r. So if I square back the two sides, get them back into this form, I get this as the equation of a circle. So this tells me what x and y, how they have to be related, given all these fixed quantities, h, k, and r. R will be a constant as well. All right. So this will give me one equation in terms of x and y, which will change when the other changes. One will change when the other changes. And that equation will define a circle. Okay, so for the special case of a unit circle just has radius equal to 1. So let's just write that out here. 1, 1. Change the. Okay, so here's minus 1. Here's 1 and here's minus 1. So it looks like this. Just a little bit so it. Okay, so the coordinates of x here are 1, x is minus 1 here, and y is 0. So, and here it's the other way, 0, 1, and 0, minus 1. So that's the unit circle. Its center, so the radius is 1. And the center is at 0, 0. It's right at the origin. Okay, so h is 0, k is 0, r is 1. And then this equation becomes x squared plus y squared is equal to simply 1 squared, which is 1. So that's the equation of a unit circle. Okay, and anyway, the question that they ask in the textbook and they solve for you is, given this equation of the unit circle, find y as a function of x. Okay, so now when we try to do that, so we'll put the x squared on the other side, and you get 1 minus x squared. Right? And then you're trying to isolate y on one side and put everything else on the other, constants and x's and anything else. Now when I have y squared here, now I can take the square root of both sides and I just get y. So I just want to make it y is equal to something. But because I take the square root, I have to include plus or minus the square root, the standard square root of 1 minus x squared. The standard square root is always positive. Now this is not a function, notice. Why? Because I have two possible values for each value of x. Okay, on the graph, if you look at the graph, you can see that right away. If I have a single value of x over here, for example, along the x-axis, somewhere between 0 and minus 1, then you'll see when I go up to hit the curve to find the y value, right? I can't just take y to be 0. I have to go up to the curve, and that tells me the value of the function. So I go up to the y value. There are two places I hit. So I have two values, all right? And that's not a function. But I can take one of these two, call them branches. Okay, I can take the upper branch, and that is a function. So that positive square root by itself, the upper branch, is one function, and then the other function is the negative square root. So I can break this thing which is not a function, up into two things which are both functions separately. They're different functions. So one is the upper semicircle and the other is the lower semicircle. And you put them together and you get the entire circle. All right. Now what I did here was an important thing to note, okay? What I did here was I drew a vertical line, and I checked that I had that vertical line crossed the graph in two places, all right? And that told me that it's not a function. Okay, so that's called a vertical line test. Okay, it would be a function if every vertical line, for example here, every vertical line intersects the graph only in one place. Where I only go where value of x which have a value for y. Okay, likewise here, there's only one place where the vertical line going through each value of x on the x-axis will hit the graph. So there will only be one value for y. Okay, so if every vertical line intersects, every vertical line intersects the graph only in at most one point, then it's the graph of a function. Otherwise, if there's only one line in the whole graph which intersects in two, then it's not a function. If I can find one vertical line which intersects in two or more places, then not a function. Okay, so it's a very specific criteria. If I can just find one vertical line which intersects in two, then it's not a function. Here I can find many vertical lines which intersect in more than one, two or more. So I can see easily that it's not a function. But that means something like this is not a function, where you have a curve here and a curve here, and just those 2 points are associated with 1, then that's not a function. Okay, if it had an open dot on one of them and a closed dot on the other, then this point is not included, this point is, then that would be a function. Okay. All right, so it's getting out to be 15 minutes here, so I think I'll quit for now at this point. So next time I will, if you have any questions and it's hard to interrupt me because of the internet or whatever, then feel free to ask a question. You should indicate the time when I said it in the lecture, so that it's easy for me to find where I said that, and I'll try to answer your question as soon as possible. So next time we will talk a little bit more about implicit functions, and then I'll give some more examples of evaluating functions and solving for particular values of functions, and also looking at what happens from the graphical standpoint. In other words, how to do that graphically. And we'll also talk about one-to-one functions and the horizontal line test. Okay, so I'll post some homework as well. I've written down some homework to start out with, but I'll post that as well when I give maybe just before I give the lecture. So this lecture will be posted, and I'll probably give it to the class in the session coming up, roughly 12 hours from now. So in your evening, at about 7 o'clock, I guess is what we said. Okay, that seems to be what people want to stick to for the most part. Okay, so I'll give this. I'll just give this video, and if people have questions during that, they can ask it, interrupt the video, or I'll just post it online. They can watch it and then ask questions during that next session. Okay, so if no other questions, then if you can't make it, or if your internet is poor at that time, then please again ask by email. Okay. All right. So that's all for the first lecture. Thank you.